Last time, we built the tower. Talk, then think, carried up a glowing highway 96 times. But I left you on a cliff. That tower cannot read your raw text at all. Before it can do a single thing, your words have to become ordered tokens, chopped into pieces and stamped with their order. Today, we do both. We turn raw text into ordered tokens. And we start by answering a question that has embarrassed the smartest machines on Earth. Watch this. Ask the model that writes flawless code one tiny thing. How many R's are in the word strawberry? It thinks. It answers confidently, 2. The correct answer is 3, and this is not a fluke or a dumb model. The very same system that can write you a working compiler will look at strawberry and miscount its letters like a tired child. People build a whole meme out of it. The easy explanation is that the AI is secretly stupid. That explanation is wrong. The real reason is far stranger, and it has nothing to do with the model you spent 6 episodes building. The mistake is made before the model ever runs. By the end of this video, 3 things. You will know exactly why a genius can't count to 3, you'll have watched a real word physically collapse into the pieces a model actually sees, and you'll understand the single algorithm behind every chatbot you've ever used. The twist? It's the same trick we used to shrink files, invented in 1994 to save disk space, decades before anyone dreamed of GPT. And then, at the very end, we'll fix the second half of the cliff, because chopping the words is only half the job. The tower also has no idea what order they came in, and before we're done, we'll stamp that order on 2. 1 algorithm, 2 completely different jobs, and 1 final trick to give the model a sense of order. Let's go meet the layer. Everybody skips. Start with the failure, slowed all the way down. To you, strawberry is 10 letters in a row, and counting the R's is trivial. But the model never sees 10 letters. The word snaps apart into 3 glowing chunks. Roughly, then raw, then berry. That's it. That's the whole word, to the machine, 3 pieces. Now try to count the R's. They're buried inside raw and inside berry. The model isn't looking at letters at all, it's looking at these. And you can't count what you can't see. So where did these chunks come from? Let's place this step in the machine. Here's the whole pipeline you've been building. Your text comes in on the left. Then it hits a box we have never once opened. The text gets chopped into pieces, the pieces get turned into ID numbers, and only then do those numbers become the vectors from episode 3, which flow into the tower from last time. Everything downstream you already understand. But that box, the chopping, is its own separate machine with its own rules. It's called the tokenizer, and today we finally open it. Remember the core fact from episode 3. A neural network cannot read. It does math on numbers, and only numbers. So before a single word reaches the model, every piece of it has to be swapped for an ID, a row number in a giant lookup table. That table has a fixed size, decided in advance. Which means we face one deceptively hard question. What should the pieces be? How do you chop human language into a fixed list of building blocks? Get this wrong, and the smartest model in the world inherits your mistake. So let's try the 2 obvious answers and watch both of them break. Obvious answer 1, 1 ID per word. Cat is a token, dog is a token, simple. But language doesn't sit still. The very first time it meets a name, a typo, a new product, or a word in another language, there's no row for it. It falls into a single useless bucket, the unknown token, an information black hole. And the list of all possible words is endless, millions, and growing. A vocabulary this size is both too big and full of holes. Words alone are too coarse. Scratch that. Obvious answer 2, go the other way, 1 ID per character. Now you can spell anything, 26 letters, some punctuation, done. Nothing is ever unknown. But watch what happens to a normal sentence. It explodes into a ribbon of tiny tiles, 1 per letter. A single long word like internationalization becomes 20 separate steps. And remember, attention has to compare every piece to every other piece. More pieces means brutally more work. Plus, the model now has to relearn how to spell from scratch. Characters are too fine. We've found the 2 walls. The answer has to live in between. This is a Goldilocks problem. Whole words are the chair that's too big. Single characters are the chair that's too small. We want the one in the middle. Pieces bigger than letters, so a sentence stays short. But smaller than words, so we can still build anything we've never seen. Common stuff should be 1 fat tile. Rare stuff should fall back to small ones. The question is just, how do you find that perfect middle automatically, without a human writing the list by hand? And the answer is a trick you have already watched me run. Cast your mind back to the compression video. To shrink a file, we hunted for the most common pair of symbols sitting side by side, and we glued them into a single new shortcut. Then, we did it again, and again. Find the most frequent pair, give it one symbol, repeat. That exact move has a name: byte pair encoding. And here's the part that should stop you cold. That is the same algorithm, unchanged, that builds the vocabulary of every GPT. We are about to use a file compression trick to teach a machine to read. Let me show you it actually run. Forget billions of words. We'll learn the rules on a tiny pretend corpus, just 5 words with how often each appears. Hug 10 times, pug 5, pun 12, bun 4, and hugs 5. We start at rock bottom, with every word split into single characters, and our entire vocabulary is just the handful of letters that show up. That empty table on the right is where the magic gets written. It's called the merge table, and right now it has 0 rules in it. Our whole job is to fill it, 1 row at a time. Round 1. We sweep across every word and count every adjacent pair. The pair you hear in the middle of hug, the ug sound, also shows up in pug and twice in hugs. Add it all up across the corpus, and that one pair appears 20 times. Nothing else comes close, so it wins. We glue those 2 characters into one new piece, ug, and we write our very first rule into the merge table. Now look at the words on the left. Everywhere they were spelled out letter by letter, the 2 characters slide together and fuse into a single ug tile with a snap. The words just got shorter. Round 2. Same move on the new shorter words. Recount the pairs. This time, the winner is the un sound, the pair sitting inside pun and bun, 16 appearances. So we merge it into a single un tile, the second rule written into the table. The pieces glue together on the left again. Notice the rhythm. Count the pairs, crown the winner, glue it, log the rule. Count, crown, glue, log. The table is getting taller and the words are getting shorter, in lockstep. That is the entire algorithm, and you just watched it tick twice. Now, round 3, and this one is beautiful. We recount, and the winner is the pair that glues an opening H onto the ug tile we just made 15 times. But look closely at what we're merging. That ug isn't a letter anymore. It's a piece we invented 2 rounds ago. So gluing onto it gives us the whole word hug as a single token, assembled out of earlier merges, like a thing built from smaller things you already made. A real word born from the algorithm, not handed to it. The table now has 3 rules. And the moment of clarity is this. That growing table of rules? That is the tokenizer being born, line by line. And here's the only question left. When do you stop? You stop when the table hits a target size you picked in advance. Each merge adds exactly 1 new piece to your vocabulary, so you just keep gluing the most common pair until the vocabulary is as big as you wanted, then freeze it. More merges means longer, smarter pieces but a bigger table. Fewer merges means a smaller table but choppier text. You're dialing in that Goldilocks middle by hand with 1 number. Stop, and the merge table is finished forever. It will never learn another rule. Now slow down, because this is the idea everything else rests on. Most people picture a tokenizer as a dictionary you look words up in. It is not. There are 2 completely separate stages here, and they happen at 2 completely different times. What you just watched, building that table by reading a mountain of text, happens once, offline, long before you ever type a word. That's training the tokenizer. Using it on your actual sentence is a totally different act. Confusing these 2 is where everyone gets lost. So let me give you the picture that makes it click. Think of a recipe book and a line cook. Training the tokenizer is writing the recipe book. You read an enormous amount of text once, and you write down which pairs to glue in exactly what order. That book is the merge table. Then comes the line cook. When your sentence arrives at the restaurant, the cook never invents a new recipe. They just open the book and follow it, top to bottom, on whatever ingredients showed up. The cook is fast and dumb and never improvises. All the intelligence lives in the book, and the book was written long ago, and it never changes. Let's be the line cook. Here comes a brand new word the tokenizer has never seen as a whole: bug. First, we shatter it into single characters. Then we open the recipe book and run a playhead straight down it, top to bottom. First rule, glue the UG pair. Does it match? Yes, the back of bug fuses into a single UG tile. Second rule, glue the unpair. No match here, skip it. Third rule, the HUD rule. No opening to merge, skip. We hit the bottom of the book. Done. Bug became just two pieces, a lone first character and UG. We tokenized a word we'd never seen, with zero guessing, just by replaying the rules in order. Sit with how clean that is. There is no magic lookup, no special case for new words. The merge table is the entire learned artifact. The whole tokenizer is just that list of rules, plus a cook who replays it. And because the cook can always fall back to single characters when nothing matches, it can chop any text on Earth into pieces and never gets truly stuck. That's the heart of it. Now, let me show you the two small upgrades that turn this toy into the thing inside actual GPT. Upgrade 1. We started our toy from characters. But real GPT starts one level deeper, from raw bytes. Under the hood, every character you can type, every emoji, every alphabet, every line of code, is ultimately just a stream of bytes, and there are exactly 256 possible byte values. That's it. The whole of human writing, every language at once, is built from a base set of just 256 things. So you start your vocabulary with all of them, and merge up from there. And this quietly kills the unknown token problem forever. Drop in an emoji, or a word in a language the tokenizer has barely seen. It can't find a big tile for it? Fine. It shatters into its raw bytes, and every byte is already in the vocabulary, guaranteed. There is no such thing as a word that can't be encoded, because in the worst case, anything becomes bytes. 256 starting pieces, and from them, every text that has ever existed or ever will. That black hole from the word level idea? Sealed shut. Upgrade 2 is sneaky, but it matters. The original compression trick would merge across anything to shrink a file. It would happily glue the end of one word onto the period or the space after it, but for language, that's nonsense. You don't want dog fused to the next comma. So real GPT first slices the text along word and punctuation boundaries, then only ever merges inside those slices. This is the one place it breaks from pure compression. The file shrinking version wants the smallest file. The language version wants the most useful pieces. Same engine, smarter rules. Put it together and you get the real artifact. GPT-2's vocabulary is a famously clean number. 256 raw bytes plus 50,000 learned merges plus one special marker that means end of text. Add them up and you land on 50,257 tokens. And that's the whole tokenizer. A fixed list of pieces, each with an ID, plus the merge table that produces them. Those ID numbers are exactly what gets fed into the embedding table from episode 3. The chopping is done, the handoff is complete, and these vocabularies have been quietly ballooning. GPT-2 used about 50,000 pieces. GPT-4 roughly doubled it, to around 100,000. The newest model doubled it again, to around 200,000. Why bother? Because a bigger vocabulary means longer, fatter tiles, which means fewer tokens per sentence. And fewer tokens means it's cheaper to run and it fits more of your document in memory at once. Watch the little counter on the side. As the vocabulary grows, the same paragraph chops into fewer and fewer pieces. Bigger book, shorter sentences. Now let's go collect the payoff I promised you and finally close the strawberry case. You now know precisely what happened. When the tokenizer trained on a mountain of English, the chunkberry was wildly common, so it got promoted to a single fat tile. So did raw. By the time your word arrives, strawberry doesn't get spelled out. It gets served as sta, then raw, then berry. The individual R's were swallowed inside those tiles back when the merge table was built. Asking the model to count them is asking it to count something it genuinely cannot see. The bug was never in the brain, it was in the chopping. And the same crack causes a quieter, more unfair problem. The merge table was trained on mostly English text, so English got all the fat, efficient tiles. The word "the" is one token. But write the very same sentence in many other languages, and the tokenizer has no big tiles for it, so it shatters into far more pieces. The same meaning, the same question, can cost 2 to 3 times as many tokens, and for some languages even more. And since you pay per token, that means the exact same request literally costs more, runs slower, and fits less context, purely because of how it was chopped. And it gets genuinely weird. Remember, the tokenizer and the model are two separate things, trained on two separate piles of text. So a strange piece can sneak into the merge table from some odd corner of the internet. a piece the model itself almost never saw during its own training. The tokenizer knows the tile exists. The model never learned what it means. Researchers found exactly this. Certain rare tokens that, when you type them, make the model dodge, babble, or insult you because it's holding a word it was never taught. Living proof that the chopper and the brain are two different machines that can disagree. And step all the way back, because this is the real lesson of the whole tokenizer. Half the famous ways AI looks dumb, can't spell, can't count letters, fumbles big arithmetic, struggles in your language are not the model being stupid. They are fingerprints of a decision made before the model ever woke up in this one humble algorithm. The bug is before the AI. And the same idea cuts the other way. Spell the word out for it, letter by letter, and watch the failure simply vanish, because now it can finally see the letters. But we still owe you the other half of that cliff. The chopping is done. The order is not. Remember what I promised at the start. Turn raw text into ordered tokens. We've done the chopping. Now the order, and this is the part that genuinely surprises people. The tower we built has no inherent sense of order at all. Watch, feed it the cat sat, now feed it sat the cat. To attention, those are the very same bag of 3 tokens, just shuffled, and it reacts to both in the exact same way. The same vectors go in, the same answer comes out. Position is invisible to it. A model that can't tell the cat sat from sat the cat is, frankly, useless. So we have to put the order back in by hand. Here is the fix, and it is shockingly direct. Each token is already an arrow, the embedding vector from episode 3, a point in the galaxy of meaning. So for every slot in the sentence, position 1, position 2, position 3, we build one more arrow, a position signal, unique to that slot. And then we simply add it on. The token's meaning arrow, plus its position arrow, tip to tail, lands on a new arrow. That sum is what actually enters the tower. Same word, but the version at position 1 and the version at position 5 are now 2 different arrows. The order is no longer floating outside the model. It's baked right into the vector. And sit with how clean that is. We didn't bolt on a new machine or change a single block in the tower. We just nudged each arrow a little before it climbs by an amount that depends only on where it sits. Now, when attention compares 2 tokens, it isn't only comparing what they mean. It's comparing what they mean and where they are. The cat sat and sat the cat finally point in different directions. That one addition, a position signal stirred into every token's vector, is how a transformer gets a sense of order. The chopping gave us tokens. This gives us ordered tokens. Both halves of the cliff paid off. So let's close every loop. A network eats numbers, not letters, so text must be chopped first. Words are too coarse, characters too fine, so we find the middle. We find it with one trick, the same one that shrinks files. Glue the most common pair, write the rule, repeat until the table is full. Training writes that recipe book once. Encoding is just a line cook replaying it, falling back to 256 bytes so nothing is ever unknown. The chunks it produces, not letters, are the deep reason a genius can't count to 3. And because attention is blind to order, we stamp each token's vector with a position signal, so the tower finally knows what came first. Raw text, in. Ordered tokens, out. And now, pull all the way back and look at what we've actually got. Tokenizer, snapping the text into pieces. Embeddings, turning those pieces into vectors. A position signal, stamping each one with its place in line. Attention, letting the ordered words talk. The block, talk then think, stacked into a tower. And an output at the very end. Every dark slot from this whole series just lit up. The last missing piece slides into place, and the entire machine glows from end to end. There is nothing left to build. Every single part of a working GPT now exists right here on this screen, which leaves exactly one terrifying question. If every part is built, what's actually stopping us from just wiring them together and pressing train? Nothing is stopping us. That's the unsettling answer. The whole machine is sitting here, fully assembled, and every weight inside it is still pure random noise, exactly as I warned you 2 episodes ago. It can chop your text into ordered tokens perfectly and understand absolutely nothing. So next time, we throw the switch. We feed it the entire internet and force it, one tiny nudge at a time, to actually learn. We press train.